In this screencast I'll show you the example of a PID control loop simulated in the Simulink environment. And what you can see on the screen is a setup for a feedback control loop, and there's various elements that go into this. For example, there's the controller gain, and then we have an integrator, something to give the derivative. We also have 1 over TR, 1 over the reset time, and we also have TD, which is the rate time. At the moment they're set to 0, so at the moment we've purely got proportional control. We also have a transfer function to show how the valve responds, a transfer function to show how the process responds to a given change in input. There's a delay which represents the dead time in the process, so although you might make a change, there'll be a bit of time in between that change actually coming into effect from when it's actually first put into the system. There's also a lag in the way the measurements are taken due to the way the instrument responds. We have a scope to look at the response, and then there's also a set point change here, which just basically immediately goes to a value of 1 to the set point there, and there's a comparator here to see the difference between the set point and what the instrument is reading. So lots of different elements and components that have gone into this. If we press run, we can see the response in the process based purely on proportional control, and you can see that there's an offset between the actual response of the PID control loop and the set point. So that offset is due to the fact that we've got only P control, and you always see that with P control. So we'll close that scope there for now, and what we need to do as a first step towards tuning this is actually get the response to regularly oscillate and kind of almost form like a sine wave, and we do that by increasing the controller gain. So we'll increase that to 2, run the process again, look at the scope, and now it's starting to oscillate, but these aren't regular oscillations, they are starting to go down towards the set point. Okay, so again we can carry on. We'll go to 3 now and just keep increasing this, and now we see we've got oscillations, but they're getting larger and larger. So we can see from that we need to be somewhere in between 2 and 3 for the controller gain to get this the gain for marginal stability. And in fact I can tell you that it's going to be 2.31 for this situation. We'll run the simulation again. You just have to keep playing around with this until you get the right value, but this is now our KCM value, so capital K subscript CM, and that's the gain for marginal stability. And we can click on this measurement tab here, and we can move these bits around until we find the difference from peak to peak, and this is referred to as the ultimate period, and it's a little bit tricky. We might need to zoom in a little bit on here to be able to see a bit better, and once we get those at the peaks we can then see the difference in time is 6.293, and that then is the value for P subscript U, the ultimate period. And we've also worked out the controller gain for marginal stability at 2.31. We can see that's the value we put into here. Those two values are really important because then we can use those to actually tune the PID control loop, and I'll show you how to do that in the next video.